Welcome back to Josh Does Math. In this video, we're going to be doing a problem that's related to the tangent of the curve y is equal to 1 over x. So here's the problem right here. Let P be a point on the first quadrant part of the curve y is equal to 1 over x. Show that the point determined by the x-axis, the tangent at P, and the line from P to the origin is isosceles, and find its area. So there's a lot going on here, but we're going to start off with just drawing the curve. We're just looking at the first quadrant right here, and there's our curve y is equal to 1 over x. And we're picking some point on it. We'll call it P, but we're more interested in the coordinates at that point. So the coordinates there, we'll just call it A, comma. I would call it A, comma B, but we can figure out what the other value is, what the y value is based on A. Since y is equal to 1 over x, this is going to be 1 over A. So that'll be our point, A, comma, 1 over A. And we're looking at the tangent at that point. So we'll say that's the tangent. And we know the tangent's going to cross right here, so that's another point. And we're also looking at the point from the origin to the point that's on the curve, P. And although this might not look isosceles, this triangle is supposedly isosceles, and our goal is to prove it. So we know another point right here that's going to be 0, 0. And we don't know what this point is yet. So how do we even begin to start this? Well, maybe we should find some equations of the lines. How about the equation of the tangent line? That might be helpful. Certainly won't hurt. So what is the equation of the tangent line? Well, we know it's got the same slope as the curve, so take the derivative of the curve, that's going to be the slope of the tangent. So dy dx is equal to d. I'll write 1 over x as x to the negative first power. That'll be helpful whenever we go to use the power rule for derivatives in this next step. So the power rule says power out front, 1 smaller on the power. And then we can just rewrite this as negative 1 over x squared. And what is the derivative at x is equal to a right here? I'll call that m for the slope of the tangent. And I'm just going to plug in a for x. So I get negative 1 over a squared. That's the slope of the tangent. Now, if I knew a point that the tangent line went through, we could set up point-slope form and figure out the equation of the line. Well, this is convenient. The tangent goes right through a, comma, 1 over a. Y minus 1 over a is equal to negative 1 over a squared, that's m, times x minus a. So now I'm just going to set this up so that y is equal to something x plus something, slope-intercept form. So this becomes y is equal to negative x over a squared plus 1 over a plus 1 over a. So that's y is equal to negative x over a squared plus 2 over a. So this is my equation of the tangent line. So can we figure out what this point is right here? Well, if I just plug in 0 for y, sure, I can find the x value. 0 is equal to negative x over a squared plus 2 over a. X over a squared is equal to 2 over a. Just isolate x. We get x is equal to 2a. So this point right here is 2a, comma, 0. So can I figure out any of the lengths of this triangle right here? Well, I know this one, this length right here, that's just going to be 2a. So there's one length of the triangle. What about the other ones? I can use Pythagorean theorem right here to figure out this length. That's going to be a squared plus 1 over a squared, all under the root. And that can simplify down a little bit. We can say root of a squared plus 1 over a squared. And we can multiply the top and bottom by something, pull out a common factor, which I'll do. So this will be a squared times a squared over a squared plus 1 over a squared. So I just multiplied and divided by the same factor over here. And I can pull out this factor of a squared in the denominator. So this becomes root of a to the fourth plus 1 all over a squared. So that's my other side length. What about the third one right here? Well, I can use the distance formula to figure that out. So that's going to be 2a minus a squared minus 1 over a minus 0 squared. And I can simplify that as a squared minus 1 over a squared. And as we saw, I just simplified that over here, so this will simplify exactly the same way. And we get root of a to the fourth plus 1 all over a squared. So as you can see, these two side lengths right here are the exact same length. So we can prove that this triangle is isosceles because they're the same length. Now how do we find its area? Well, that's easy. The area for any triangle is just 1/2 base times height. So we just set this up as 1/2. What's the base? That's going to be 2a. And what's the height? That's just going to be 1 over a. That's this distance right here. I'll say that this is my area, capital A. So now I just do some simplification here. 1/2 cancels with 2, a cancels with 1 over a, and I'm just left with 1, which means that for any arbitrary point on the curve, y is equal to 1 over x, the triangle formed by these special lines here is always going to turn out to be just 1, no matter where you put this point on the curve, as long as it's in the first quadrant. So that's just a neat little thing that you can find by finding the equation of the tangent and creating the triangle out of these specific points and lines. Thanks for watching.